Hi, welcome back. So if you're here, you're probably here for Haskell, or Haskell, or however you pronounce it. But before we get to that, for today we just have a few announcements, and then we'll go straight into the lab. And then some announcements, the roundtable that we've been talking about all term is being moved to B term due to timing with other clubs. And then on Monday, UP is having the Burn the Midnight Oils, which is where a bunch of CS people just kind of get together and try to finish all their projects for final, usually. But
we're also there to help you guys out if you need help with anything.
Or if you need a de-stressor.
Or if you need a de-stressor.
And this is the last, yeah.
What is the roundtable?
We were trying to get all the CS clubs on campus together in one room, basically. Yeah. And then no meeting next week. That means this is the last meeting of the term. And good luck on your finals for this upcoming week. And you can take over.
Cool. So I made a nice pretty presentation. Unfortunately, Acrobat won't let me put it in full screen, so you're going to have to deal with this Chrome around it. Sorry. So this is a Haskell language lab. I'm Barry DeLech, for those of you who don't know me. This is my email address, Slack. If you want to get in contact with me, I'll also put them back up at the end. I titled this a whirlwind tour because I don't have time to teach you everything there is to know about Haskell. There's kind of a lot, and I only have an hour, minus all the time I wasted trying to get this up. So it's going to go kind of quickly. If you don't get anything at any point, please interrupt me and ask, because you're just going to get more lost. So please, please, please interrupt me if you need to. I won't be offended. So getting into it, here's what this talk is going to look like. First, I'm going to talk about why Haskell is cool, what's unique about it, what's interesting, then some basic syntax, common built-ins, and then I'm going to talk about monads, which are one of the most interesting things about Haskell that is kind of difficult for a lot of people. So we'll see how I do. And then questions at the end. This may or may not take the full hour. It's hopefully not going to. And so leaving time at the end for just regular questions, also to kind of go in the direction that you guys want. Because there are a lot of directions I could go with this, but I'll leave that up to you guys and then kind of just wing it. Cool, so getting into it, why Haskell? Haskell is a purely functional language. That means that you have functions. I'm sure all of you have taken 1101, I think it is, 1110, the one with Racket. Racket is a functional language. Racket, however, is not a pure language. Racket pretends to be sometimes, but it's not always. Because Racket has getBang and setBang and all of those fun things. I'm seeing some confused faces. You'll do that tomorrow, okay. Did this presentation too early. Okay. Racket pretends to be functional, or to be pure rather, but it actually has a lot of imperative things in it. You can have variables and set them and get them. It's just a lot of stuff doesn't do that, but the language doesn't stop you from it. So Racket is actually not pure. Haskell is. There are no variables per se in Haskell. We'll get into that in a bit more detail later as to why that's not entirely true, but for the moment, it is. You can't change anything. Once you have a variable bound, it's bound for life. It has strong static typing. And that means that you have a lot of different types, and you can't use them in place of each other. For instance, JavaScript will let you use an integer where a string is expected, and it'll automatically format it for you, which may be what you wanted, it may not. It might be because you had a bug. Some people like that, some people don't. Guess which camp I fall into? I use Haskell. I think it's much more important to know that your program is actually doing what you think it's doing, rather than having that little bit of convenience of not needing to explicitly format it. And lots of people agree with me. Not everyone, but typing is cool. And you can also do a lot more with it. That's one of the things I'll be getting into a bit more later. But it doesn't have to be just for what is this data. You can also use it for instance, proving that your program is not vulnerable to certain types of attacks. And you can actually prove that using types, which is a really neat thing that you can't do in weakly typed languages like JavaScript. Haskell, however, has type inference, which means you don't need to say what the types are. You can just say, x equals 2 plus 2, and it'll figure out what the type of that is for you. If you want to specify, you can, but it's not mandatory. And so that is also a common complaint about typed languages is, oh, I don't want to have to say the type of every single thing. That's just annoying. Well, in Haskell, you don't have to. Haskell is a very high-level language. The idiom is you can program in pure ideas. It gives you a lot of power and a lot of flexibility. You get to say what you want done rather than how specifically to do it. And that's very powerful if you've ever tried writing in C, for instance. Not bashing C, I love C, but it's not the right tool for every job. Haskell is also highly modular. I'll be getting into that more later with type classes. But it is very, very easy to write code in Haskell that will work for a lot of different purposes. More so than just having separate modules and you import this module or that module. But you can actually have code that looks at other code. And I'll get more into that later, so don't worry about that for now. Oh, by the way, I am going to be sending out these slides later, so you don't need to take notes if you don't want to. If you want to, that's cool, I don't care. But I will be sending these out. That said, I might say things verbally that aren't on the slide, so do what you want, I don't care. Haskell is also highly efficient, even though it's high level. And often that's a trade-off, right? It's very expressive, but it's slow, think Python. Or it's very hard to write in, but it's blazing fast, think C. Haskell kind of gets the best of both worlds, where it is very expressive, but it's also quite fast. Obviously not as fast as C, but actually pretty close. And it has a lot of tools that you can use to optimize it to actually the same efficiency as C, if you need performance. I'm not going to be talking about that unless you want me to at the end, but I can if you'd like. Haskell is also lazy, which is not a bad thing, despite the connotations of laziness. It means that it doesn't evaluate things until you need them. For instance, if you have, for instance, A or B in a Boolean expression, and A turns out to be true, we don't care what B is. We don't need to evaluate it. A lot of languages do that. That's short-circuit evaluation. Haskell kind of takes that to the next level and does that for everything. Every single function automatically does that. It also means that you can do stuff like having infinite lists. Not just lists that are really, really big, but you can have a list that's actually infinite in Haskell. You can have the list 1, 2, 3, 4, 5 all the way out to infinity. And that's completely okay because it only computes it as you need it. And so if you only use the first 20 elements of that list, well, it only computes the first 20 elements of that list, and that's all that you have in memory. So you don't need infinite memory to run Haskell, which is nice, because our computers don't have infinite memory. Thank you. Because it's lazy, it also gets automagical concurrency. And what that means is it can automatically parallelize your computations in a way that looks like magic. For instance, if you have A plus B, where A and B are two really complicated expressions, because Haskell is pure, and it knows that there can't be any side effects from either A or B, it can evaluate them A and then B, or it could do B and then A, or it could do them both at the same time. And so it, hold on a sec, and so it will, most of the time. It will evaluate both of them in parallel to speed up the computation if you have multiple cores on your computer. Yes?
You answered it a second. I was going to ask if it was pure parallelism or if it was just concurrency with the name of parallels. But
So you can also do parallelism. That's a thing that I can talk more about later. That is a bit more difficult, but also it will do a lot of that automatically. For instance, if you are mapping over a list, it will automatically parallelize that over the list because it can. It's pure. If you want to do more complicated things than that, you need to tell it to explicitly, but you can, and it's not hard. Any other questions before I move on? I think this is the last one on the slide. Cool. So now let's move on to some basic syntax. Most basic thing is variables. So I've got the string hello world, and that's assigned to the variable greeting. Except here's the thing, is remember how I said Haskell doesn't have variables? Haskell doesn't have variables. These are actually bindings, not variables. The difference is kind of semantic, but basically we're saying we're giving the name greeting to the string hello world. We're putting a name tag on it, so to speak. And you can never take that name tag back and give it to someone else. It's not a variable per se. That said, lots of people call them variables. I will probably call it a variable at some point during this talk. I will try not to, but if I say variable, just know that I mean binding. And if we wanted to, we could specify a type signature for this. We don't have to, but we could. And it's generally good practice to give type signatures to your top level bits of code, meaning if you're writing a library, anything that's exposed to the user, just so that they know, looking at your code, okay, this is how this works. Even though the compiler can tell them for you, it's easier for them just to have it right there. And so the way you do that is you say greeting, double colon, just means has the type of string. Question?
So it's similar to like a C macro, except that has a type.
Yes.
Okay.
Yes, similar to a C macro, except it has a type and can't be undefined. C macros, you can technically undefine them. Doesn't usually happen, but can. Haskell, you can't. Yes?
Can you do that as one line?
Yes and no. So technically no, but what you can do is say that the string hello world is of type string, and that's what you're binding to greeting. And so technically you aren't giving the type string to greeting, you're giving it to the value of greeting. So yes and no. And the way you would do that is just by moving the double colon onto the next line. You say greeting equals hello world double colon string. And that can sometimes be useful when you have more complicated expressions and you want to give a type signature for something on the inside. You just put it in parentheses, say double colon, whatever it is. That actually is useful at times. But like this, not really. Cool, and then we also have functions are also pretty important in functional programming. Just kidding, not functions yet. So suppose we realized, oh, we forgot the exclamation point in hello world. We're not excited enough. And for some reason, we don't want to go back and edit our code. We can say excited greeting equals greeting, which we previously defined. Double plus just means append the exclamation point. And so this shows two things. One, that we can just use our variables just like you would expect, and it's the exact same as just putting their value in. It also shows that we can assign complicated expressions, or in this case, not so complicated expressions, to bindings. And now we have functions. So functions look a lot like variables, or non-function bindings, because functions are actually just regular old bindings. Or alternatively, regular old bindings are just functions that take no parameters. Whichever way you choose to think about it, they are actually the same thing under the hood. And so the only difference is now we say greet user name equals hello plus name plus exclamation point. And so what that's saying is greet user is a function, takes a parameter name, and gives you the type, and gives you the value hello, whatever, exclamation point. Does anyone want to guess what the type of this is? That's okay. So the type of this is actually string arrow string, meaning it takes a string as an argument, and then spits out a string as a result. And so the way we use this is exactly the way it's defined there. We say greet user and then put a string there. So for instance, we could say greet user, quotes, Barry. And that is exactly equivalent to writing, hello, Barry. Any questions so far? Okay. Now, not all functions are just of one parameter, obviously. So we can do multi-parameter functions also. Let's say we're making the append function. Takes two strings, sticks them together. Anyone want to guess what type this has? I heard a couple of things all kind of mushed together. If you said string, arrow, string, arrow, string, you were correct. That was a trick question. Don't be hard on yourselves. I wasn't expecting you to get that right. So this looks kind of confusing. Do we have two functions? What's going on here? And the answer is, yeah, we do actually kind of have two functions. Because the way that this actually is parsed under the hood is with the parentheses here. So really what append is it's a function that takes one parameter and gives you a function that takes another parameter. And so you really only have functions of one variable. It's just two functions mushed together. And so that's called currying. It's a really powerful concept, used in some languages, not so many, named after the mathematician Haskell Curry. Has two things named after him. Very cool. And that is useful in a lot of ways. I'm going to get to a few of them pretty soon, actually. Right here, actually. So suppose we want to write a function to add a prefix to something. Well, we've already got append, right? So how do we do that? In most languages, we would write something like this, right? Add prefix, adjective, equals append, Haskell is that adjective. And that works. You can do that in Haskell. It's not wrong. But it's not the Haskell way to do it. The Haskell way to do it is just to leave off the adjective. Because remember, append is a function that takes one parameter and then returns a function that sticks that parameter onto the beginning of another parameter. And so the Haskell-y way to do this is actually just to say add prefix equals append string Haskell is. Does that make sense? I see a lot of confused faces. Yes?
So is that to say that anytime we call a function, not only we get a function back, but if that function happens to take a variable number of arguments, we can continue adding those arguments?
You can't have a variable number of arguments in Haskell. Every type has, or every function has a defined number of types. There is no varargs. If you want to emulate that, you can use lists and stuff, but natively Haskell does not do that because that kind of compromises your type safety.
So is that to say then that if you do something with an incomplete number of arguments, i.e. here we're doing one argument instead of two,
yes.
It will return a function with n minus one
Yes.
arguments?
Yes, that is exactly right. Good question. Anyone else? Any questions? Okay, cool. Question.
By removing, because you know that adjective is only one variable, you can remove it, is basically what this is?
In this particular case.
Okay.
In other cases, it may be more complicated than that.
Okay.
But the key takeaway from this is that when you have a function that takes multiple parameters, even though we say it takes multiple parameters, really under the hood, it's a function that takes one parameter and gives you another parameter. And this is just a byproduct of that. We can do this neat thing, even though you can't in most languages.
Okay.
Because most languages actually have functions that take multiple parameters. Yes?
And I assume this is the answer, this is why type signatures are useful, but how, looking at that line, would I know, say I didn't know append had two arguments,
Yep.
How would I know I need to call add prefix with another argument?
That's exactly why type signatures are useful. So if you were to just, I can't cover the computer screen, if you weren't to have this line, and you were to just have that, a person reading that code wouldn't know. You could load that into an interpreter, because Haskell also has an interpreter. I'll also talk about that towards the end if you need it. or if you ask for it, rather. And you can say, what is the type of this thing? And just ask the interpreter / compiler, just what is the type? Tell me. You know, tell me. And you can do that. Haskell also has really powerful built-in documentation. It can actually generate documentation from your code and from the type signatures, even if you don't specify the type signatures. It's called Haskell. I'm not going to talk about that much unless you ask me to at the end. But basically, if you run Haskell on this code, it will give you a nice, pretty HTML document that says add prefix is of type string arrow string. And it will have all sorts of fancy hyperlinks and everything. And even if you don't give the type in your code. Does that answer your question? Cool. Yes?
Suppose you wanted to put the adjective before the string Haskell is, how would you write that?
Okay. No, I was hoping someone would ask that. So there are two ways to do it. You could do the same thing as, you could do this one, and just give it a parameter, and just do it the old-fashioned way. There is also a function called flip. I will get into that a bit later, but it takes a function of 2 parameters and just flips the arguments. So you could say add prefix equals flip append Haskell is, or flip append is cool, so that you have a noun at the beginning. Either one would work. I'll get to flip in a bit. That's coming up several slides from now. But yeah, you could do it either way. And both ways have their benefits, right? Doing it this way, that way, is potentially easier to understand, but doing it with flip is a lot cooler. It also, I say that in jest, but when you're familiar with Haskell, it actually doesn't look all that strange. You just kind of read that normally once you get used to it. Very good question. Any other questions? Cool. So yeah, we've got that. Oh, and operator sections. So if we look up at the definition of append, right, append is basically just our ++ operator, right? We're not actually writing a new function there. We're just assigning a new name to the ++ function. And well, didn't we just say that you don't have to give parameters if you don't need them? And the answer is yes. Yes, we did say that. So you can actually say append equals ++. You need to put it in parentheses to say I want to use this as a regular function, not as an operator. But this gives you exactly the same effect as up at the top, append s1, s2 equals s1 ++ and s2. And it has the same type signature, obviously, because it's the same function. That makes sense to everyone? Because that's kind of a weird thing. Okay, moving on. Anonymous functions. So you may or may not have gotten to these in Racket yet. TA is saying no. These exist in Racket. They exist in all functional languages. Almost all. I don't want to say all because I know there's going to be something out there. But pretty much all functional languages have what are called anonymous functions or lambda expressions. And they're basically just functions that you didn't assign a name to. Now, in this particular case, I am making this function without a name and then immediately assigning a name to it. But that's just for sake of example, so that I don't need to put it in something more complicated. But really what this is doing is it's taking an anonymous function. That's what the slash is. It's supposed to look like the lambda symbol, right there, lambda. But there isn't any lambda in ASCII, so we just take that bit off. And so we get that. Ta-da! And so it looks strange until you realize that that's why we use that slash. And so anyway, it's saying we have an anonymous function that takes a parameter name. Arrow is the same as equals, essentially. We're saying name goes to hello plus name plus exclamation point. And so, yes?
So now can you remove name and just say lambda goes to and then your function, and then assume that it looks accept the argument?
So if the only time you use name was at the end, then yes. But as it is here, like for instance, if we didn't have the exclamation point at the end, you could do that. As it is here, how would you propose omitting name to make that happen?
You have to have two functions and then flip the second one.
You could do that, yeah. No, that would be really ugly, but it would work. And that would totally work. That said, we don't do that because that's horrible. Yes?
Haskell being automagical enough to recognize that there are variables there that haven't been defined. That's my suggestion of how it could possibly work.
Interesting proposal. Counter proposal. How would it know that you didn't just make a typo?
It wouldn't.
So would you rather have it automatically say, oh, well, I don't know what this variable is, I'm going to assume you want a lambda, or would you rather have it say, hey, I don't know that variable, why don't you either make sure that it's actually a variable or add the lambda yourself?
Oh no, I mean just having a forward slash and then everything else, and then just get the name and the
Okay.
and the call there.
Same argument, that how does it know you wanted, for instance, a single parameter lambda that has name versus a double parameter lambda that has name and nom, versus, just nom was a typo of name. And so Haskell, kind of philosophically, always errs on the side of if there's any ambiguity, if we aren't sure if the user meant this or that, don't try to guess. Make the user tell me what they want, because that's more safe. And you can see that in types, you can see that in what you just described, you can see that all over the place. Of if we aren't sure what the user wanted, then make the user tell us. Don't try to guess. Good question, though. Or good proposal, not question. Good question over here.
So would it be that basically the hello and the plus plus get grouped together as one function does the argument, and the other plus plus gets added to the end of the exclamation mark?
So that's kind of what Benon was saying. You could do that, put them in parentheses to say this is an operator section, like over here. And then, I haven't gotten to this yet, but put a period between them to say I'm composing these functions. You could do that. It would not be pretty, but you could do it. However, if you wanted to just do it in a readable way, you would do it this way. And ultimately, you do need lambda expressions for this type of thing, where it's not that easy to take out the parameters. It always can be done, and it's sometimes fun to say, oh, here's this complicated function. How do I get rid of all the lambdas and all the parameters to the function? That said, don't do that in real code, because anyone who reads it will hate you. Yes?
How do you add comments in Haskell? It's the character.
I totally forgot to put that in here. Double dash. You can also do open brace dash, and then dash close brace to do multi-line comments. Kind of like the slash asterisk and asterisk slash in C. Hold on a sec. The difference being that in Haskell you can have those nested, whereas in C and most other languages you can't. And that doesn't seem like a big deal until you try to comment out a large block of code that has a comment in it, and the comment stops halfway through, and so half of the code you were trying to comment out isn't commented out. If you've ever tried to comment out large blocks of code in C or in Java, I see a bunch of nods, you've seen that. That's not a problem in Haskell because comments nest. Just one of those little things that makes a big difference. There was another question over here. Okay.
Is that to say this is similar to SQL's comment syntax?
Quite possibly. I'm not familiar enough with SQL to know about its multi-line comments, but it does do double dash for single lines, I believe. So yes, in that case.
Lines have a C slash star.
Right, I did know that, thank you. So yeah, in terms of single line comments, yes, double line comment or multi-line comments, no. Also, you can use multi-line comments on one line, obviously. So a bit of a misnomer, but just have to point that out. Any other questions before I move on? Cool. Local bindings. So suppose we were to write a function hypotenuse, right? We have a right triangle, we know the sides of the two legs, we want to find out the length of the hypotenuse. Right, that is just a function that takes two parameters, x and y, and takes the square root of the sum of their squares, right? But this is a really complicated expression, right? This one, not so much, but in general, we could have complicated expressions. This is just an example. And so if you were writing this in another language, you would just make an intermediate variable in your function. You would say, you know, hypotenuse squared equals x squared plus y squared, and then return square root of hypotenuse squared. You can do that in Haskell too. It's just a little bit different. Actually, the first way that I don't have here is you could just make another binding. The disadvantage of that is now it's top level, and meaning it is a normal part of your code that even though you might have wanted it to belong just to hypotenuse, and you don't want it to be accessible from other functions in your module. So there are two main ways to have it locally bound. Yeah, you don't want that. The first way is using let. We just say let hypotenuse squared equals x squared plus y squared in square root of hypotenuse squared. And that operates much the way you would expect it to. Same as in Racket or Lisp, if you've done that. Fingers crossed that you've encountered this in Racket. If not, it's basically the same as Racket, except with less parentheses. The other way to do this is with a where clause. You say hypotenuse of x and y equals the square root of hypotenuse squared. Well, what's hypotenuse squared? Where hypotenuse squared is x squared plus y squared. And so these are more or less equivalent. There are a couple of minute details that differ in terms of what's visible where in terms of bindings. But for most purposes, they're the same. It's just a question of which do you want to appear first, right? Do you want the main point of your code to be that the hypotenuse is the square root of the hypotenuse squared, and then leave the hypotenuse squared as an implementation detail, or vice versa? And so which one you use is basically a matter of style. Either one would work just fine. Any questions before I move on? Yes?
Does Haskell naturally understand the caret sign as a square?
Yes, it does.
It does.
As exponents. Yes. Yes, it does. Couple slides from now, actually, I've got a whole bunch of built-in operators. And that, yes, that is one of them. Just another thing that makes it easier to work with. Not a huge deal, but it's nice to have. Oh, so before I move on, any more questions here? Okay. No,
Does
that was a
spacing
question.
matter?
Yes and no. The where has to be more indented than the thing it belongs to, so that you know that that's what the where belongs to. Other than that, no. You just generally do it this way so that it looks nice. You have the let and the in aligned so that it's semantically obvious that that in belongs to that let. But in terms of parsing and how the language is actually specified, you don't need to. It's just a good idea. Also, some people will put the in at the end of the let line. That's personal style. I don't like that. Most people don't do that, but you can. Yes?
Can where be on the same line as well?
I don't believe so, but don't quote me on that. Unlikely. Unlikely. I'll get back to you on that. Any other questions? Okay. Data types for real this time. So suppose we want to define a new data type, because that's kind of important, right? I mean, you have structs in C, you have classes in Java, you have, I think they're still called structs in Racket. We want to be able to do that in Haskell, right? And the way we do that is, suppose we want to define a shape class type. We say data shape equals rectangle int. And what that's saying is a shape can be a rectangle. We construct it with the rectangle function. That turns into a function later. And it takes two parameters and two ints. Right, one of them is going to be a width, the other one's going to be height, obviously. Before I continue, does that make sense? because this is a bunch of new things all dropped on you at once. Yes?
So is it to say we haven't defined rectangle yet, but when we do, it is a shape?
No. This is defining rectangle.
How
It is
that
saying,
defining shape?
Hmm?
How is that defining shape?
it is doing both. And so, so what it is it's saying you can make a rectangle. And if you do, a rectangle is a shape. It's kind of like implementing an interface in Java, except not. If you use that as your model, you will go wrong eventually. But it is conceptually similar to that in that you're saying this is one way to make a shape. The difference being that this is a closed world, whereas Java interfaces are an open world. Meaning, in Java, you can add new things to an interface at any time. In Haskell, you cannot add new constructors to a type. These are called constructors, by the way. Rectangle is a constructor. Yes?
Can you not make a square that's also a shape?
You could. I don't have that example, but I have triangles. And so we don't know if this is going to be a right triangle or not, so we need all three sides. Or at least that's the way I choose to express our triangles. And so this triangle has 3 ends, 3 sides. And so this might make things a bit clearer. It's saying to make a shape, or if you want a shape, the 2 ways to do it are as a rectangle with these parameters or as a triangle with those parameters. You were first.
Could you just make just a triangle then?
You could, yeah.
Okay.
If you didn't want to allow rectangles at all, you just wouldn't put that line and you would just say data shape equals triangle. If you want to construct a triangle, you just say triangle, 1, 2, 3. And that is an object of type shape.
And then you can do shape 1, 2, 3 also.
No. So the difference here is shape is the type. Rectangle and triangle are the way you make the type. If that's confusing, an analogy that may help is in pretty much every language you have ints, right? Int is a type. But you can't make an int by typing in int. You make an int by typing in 3 or 5 or 17. Those are the particular constructors of int. Those are how you make an int. They're members of int, so to speak, if you're talking in category theory. But those are the data types that inhabit or those are the data objects that inhabit the type int. I'm using some jargon there, but it means more or less what it means in English. And so in this case, rectangle and triangle are both objects that are of type shape. Does that make sense? Yes?
So let's say we wanted our data type to not have a super type. So like, I call it shape super type, I don't know what it's actually called. So like, we'll say I just wanted to have 2 types, rectangle and color.
Okay.
Is it possible to just say like data rectangle is equal to int?
No. So the way you would do that is you would say data rectangle equals rectangle int int. When you only have one constructor, you traditionally name it the same as the type, which may make things more or less confusing depending on how you think about it. But there is a distinction between the constructors, which are rectangle and triangle, versus the type, which is shape. Constructors are a way to make a type. Yes?
Is this like the where section where it has to be indented, or can they be on the same line?
They can be on the same line. If you have a lot of them, you generally don't want to. But it's totally valid to do it. Yes?
Can you make a data type that is made of shapes?
Yes, you can. For instance, if we wanted a multi-shape that has 2 shapes in it, you would say data multi-shape equals multi-shape, shape, shape. The same way that we said rectangle int int here. We say you make a rectangle with 2 ints, you make a multi-shape with 2 shapes. And when we do that, shape is just as much type as int is. It's just as first class, so to speak. Any other questions? Does anyone not understand this? even if you don't have an actual question about it. If there were a test on this, would you pass the test? Explaining this. Okay, I will move on. Feel free to stop me because I know that there is a lot of new stuff here, and there's a lot going on. Cool, so now we have that type that we defined. I'm gonna keep referencing it. And so now suppose we want to write a function that uses shapes. For instance, a function valid that says, is this shape a valid shape? And so before we look at the code, what does that do? Well, all rectangles are valid because you can make a rectangle of any dimensions you want, but not all triangles are valid, right? I can't have a triangle with sides 1, 1, and 3. You just can't make that happen. And so valid is going to make sure that you can actually construct the shape that you give it. And so that has type shape to bool, because it takes a shape and gives you a boolean. Is it valid or not? And so the way we write that, for the rectangle, which is the easy one, we say valid rectangle with height. This is deconstructing the type that we previously constructed with rectangle. Equals true, right? We don't care what width and height are, it's always true. And so then for triangles, we say valid triangle ABC equals, A plus B is greater than C, B plus C is greater than A, C plus A is greater than B. Basically, all three of those constraints. Yes?
Is there a way for the type to the function to belong to the type a la something object-oriented, or is this like closer to C where it's just a function that's in its own state?
So this right now is like C, where the functions just are there. They aren't associated with a type per se. Although you could make the argument that looking at this, well, it's obviously associated with shapes. But semantically, no. We can't do that yet. Couple slides from now, we will be able to. And you'll know it when you get to it. If not, I'll point it out to you. But that is a good question. So to summarize that, for now, no. In the future, yes. Yes?
So if you make a data structure with multiple types, like rectangle, triangle, and so on,
Sure.
you have to write the same method over and over for each different version.
If you want it to behave differently for different things, then yes.
Is there a way to specify this is a general function for any kind of shape?
So what would that look like? What type of a function are you trying to make?
No idea.
Okay, so
If they all have a color.
okay. If they all have a color, then you can make a function, for instance, getColor, that will operate on each of them individually and extract the color parameter from it. And then if you wanted to use the color in another function, you could just use the function getColor of the thing, and then you don't need to special case it for all of those. But you would need to have the special cases for how do I get the color of a rectangle, how do I get the color of a triangle. Alternatively, you could make that into two types. You can have a shape and a colored shape, where a colored shape is just a color and a shape. And then the shape doesn't have a color anymore. And that's the way I would probably do that, so that you can have the separation of concerns, so that you can say, so that you don't need to say, how do I get the color for each particular shape? You can just say, this is how you get the color for a colored shape, and non-colored shapes don't have colors because they're non-colored. There actually is a way to generalize that, to say get the color from all of them. I don't talk about it in the slides, but I will talk about it afterwards if you ask me about it. It's called record syntax, in case I don't know what I was talking about before. Ask me about that, and I will talk to you about it. Any other questions? Cool. And so, it's okay, it's okay. And so if we were to, for instance, forget to put rectangle in there, the compiler would warn us. It would say, hold on a sec, shapes valid works on shapes, and rectangles are shapes, but you don't tell me how to work with rectangles. It'll give you a warning on that. It won't fail to compile, but it will give you a warning. In fact, I think it even gives you a warning if you don't enable any warnings. That's how much of a warning it is. It's a very strong warning, because if you intentionally don't include something, it's a sign of very bad style. There are occasionally times when you might want to not include something, but those are very, very rare, and you won't need them. Say we decided that a rectangle can't have 0 length and width. So we could put that in as valid rectangle with height equal. Oh wait, there's another slide before that. Hope you haven't started recording yet, because that would be unfortunate.
Too late.
And now you've also got me saying I hope you weren't recording that. Okay, so anyway, so we've got valid rectangle of width and height equals true, regardless of what width and height are. And so if you have warnings enabled, it will warn you like, hey, you declared W and H and you didn't use them. That might be a problem. And that's useful, because a lot of the time it is a problem. In this particular case, we know it's not. And so the way we can tell it that, yeah, I know, we don't actually care what these are, they can be anything we want, is we put an underscore. Underscore is just a pattern that means anything. And now moving on to what I was going to say about, yes?
Sorry, actually, I don't know why I didn't realize this before. Is this to say that for valid, we have to pass in triangle A, B, and C? Or is that to say that if we pass in triangle A, B, and C, will be automatically put in?
That is a good question, and one that I did not really address. So I'm going to write on the whiteboard. I hope you all can read this. If not, let me know. For instance, if we wanted to make a 3, 4, 5 right triangle, we would say T for triangle equals triangle 3, 4, 5. And so this is, T is of type shape. And this is saying, you know, T is a shape, and the particular shape is a triangle with parameters 3, 4, 5. And so if we wanted to pass that into valid, then we would say, you know, like T is valid equals valid T.
So it does automatically fill in A, B, C.
Yes.
So let's say we had D, where D was, I don't know, something with a triangle that I'm not going to think
Sure.
of. If you did triangle D in your call, or sorry, TD in your call that you got on the board,
Yes.
would Haskell be smart enough to say these 3 arguments are dedicated to the triangle, and after that is anything else?
What do you mean by anything else?
So like,
Do you mean adding something to the definition of triangle?
yes, so let's say we had A, B, C, D invalid.
Okay.
And then
No, I mean up here.
No,
Are you
I
saying
mean
we
the
add
function
something else
definition.
here?
He just needs as an input.
Okay. If you were to add it to here,
Yeah, so
that would be a type error.
no, I'm saying if we were to add it to the definition.
Valid.
Oh,
Yeah.
the definition down here.
Yeah. Add it to
That would also be an error.
But if we could we put an argument after T on what we wrote on the board?
No.
Okay.
And the reason for that is that you would get type errors from both ends. In the valid side, it would say, wait a second, triangle only takes 3 parameters.
Mhm.
You're trying to use 4. And here, it would also say, hold on a minute, triangle only takes 3 parameters, but you're giving it 4.
Mhm.
And so that probably means you want to add another parameter.
Oh no, I am saying, how do we add another parameter? Can we add another parameter?
You would add it in here, if you wanted to.
Oh, so we can't have a function-specific parameter, like say taking a triangle and something else.
Okay. If you want to take in a triangle and something else, yes, you would add another parameter to the valid function,
And
just like we did way up here. There.
So it'd be
That's fine.
triangle A, B, C, D, and then in our call there we do T and then something else.
Yes.
Okay.
So yeah, you would say valid T food
Okay.
there, and your call would, your definition of valid would look like valid triangle ABC x, for lack of a better variable.
Outside of the parentheses?
Equals.
Oh, I see.
Yes,
Okay.
because it's a second parameter to valid.
I got it.
It's
Okay.
not a part of the triangle.
Got it.
Does that make sense to everyone? Because that is something I should have talked about. I'll leave that up until the end in case you want to reference it later. So, what I was saying before I remembered that there were supposed to be underscores. While these do have to be complete, meaning you have to cover every case, they can overlap. So if we wanted to say that rectangles are not valid if they have 0 width and 0 height, we could say valid rectangle, okay. We could put the W and H back and say W does not equal 0 or H does not equal 0. We could do that. The other way we could do it is to put something before it that says valid rectangle 0, 0 equals false. And so when you have overlapping patterns like this, right, because 0, 0 obviously matches the first one, but it also matches the second one. And so when you have overlapping patterns, what it does is it does the first one that matches. You can think of it as going down the list. Does this one match? Does this one match? Does this one match? That's not actually what it does behind the scenes, but conceptually they're equivalent. Yes?
Could you pass a function in there? For instance, could you say pass in a lambda that checks if it's greater than 0?
Do you mean as a separate parameter? Or
Yeah,
in
instead
place
of 0, 0.
Yes and no. You're going to get that answer a lot. So in Haskell proper, that is Haskell 98 or Haskell 2010, which are the two main versions of Haskell that are used today, you cannot do that. However, there are a number of so-called language extensions to Haskell that let you do things that you would want to do, for instance, like that. That particular one is called, frick, what's that one called? I'll tell you that later. Don't want to confuse you yet. Definitely not because I forgot. So yes and no. Not in vanilla Haskell, but there is an extension that is pretty well established that does let you do that. View patterns. They're called view patterns. Yes. Oh, and the other way that you can do that, almost forgot, is if you wanted to say they have to be greater than 0, you could say valid rectangle of width and height, vertical bar, meaning where, width is greater than 0, and height is greater than 0, equals true. You could do that also. Almost forgot to mention that because it wasn't the same form as your question. But this is the way in vanilla Haskell that you would handle that. Can you see that in the camera?
Sort of.
Okay. I'll include it as text later.
Okay.
Is pipe always included as where? Or always,
When you're doing this, yes.
not always though?
I mean, you don't need it if you don't have a condition.
Oh no, I mean anywhere you could write the word where.
Oh, no. They are different things. I'm using the same word for them because there are only so many words in the English language, but they are actually different things in Haskell. You cannot use one in place of the other in either direction. And so if you were to do this, then you would also need another case for when this condition is not true. And so presumably that would be valid rectangle under equals false. To say, if it didn't match this, then it's false. But if you didn't, then it would give you the same warning about incomplete patterns. Good question. Any other questions before I move on? Cool. Parametric types. So, in our definition of triangle, or of shape before, we're saying that you have to use ints for the side lengths. And that's not necessarily the case, right? We might want to use doubles, we might want to use floats, we might want to use something else. So how do we do that? Would we just want to make a separate type for each one? Say like shape int, shape float, shape double, and define all of those separately? Obviously, we don't want to do that. That's code duplication, and code duplication is evil. And Haskell in particular is very averse to code duplication. So we have what are called parametric types. In other words, types that take a type. So the way that would look for a shape example is we would say shape L, meaning a shape that has a length parameter that we're calling L equals rectangle LL, meaning a rectangle has 2 L's instead of 2 ints, and triangle LLL, meaning 3 L's. And so, for instance, we could say shape int, and that would be equivalent to this guy. But we could also say shape float, or shape double, or shape anything else, and that would still work. And so this gives us modularity. We can write code that works independently of the representation we choose to use. And if we were to write the valid function for this type of shape, because these are 2 different types now, and incidentally, you wouldn't be able to give them the same name because how would it know which one you're talking about? So assuming we got rid of the previous one and we have this one instead now, we would write it like this. The type signature would look like valid double colon shape L arrow bool, and then everything else would be exactly the same. We could also say valid double colon shape int arrow bool if we only wanted it to work on shapes that had ints as the underlying type. Or we can say it works for any L and do it this way. The advantage of doing it this way is obviously that it works for any length parameter you use. The advantage of doing it the other way is you can use int-specific properties, where there aren't too many int-specific properties. But suppose you were using, for instance, floats, and you wanted to make sure that the floats haven't overflowed, for instance, because that's a thing that floats can do. You would obviously need float-specific code for that, so you would say, for instance, has overflowed is of type shape float arrow bool. Does that make sense? Cool. And now this is actually answering your previous question about can you have functions associated with data. It's called type classes in Haskell. They're very similar to interfaces in Java. They are not, even though they're called classes, they are not so much like Java classes or C classes or any other languages classes. They look something like this. This is a particular example that's built into Haskell. Saying class num A is saying we have a type class, it's called num, and we're going to call the members of it A for right now. And so it has a function plus. Plus is of type A to A to A, meaning it takes 2 A's and gives you another A. So if we're talking about ints, that would be int to int to int. If we're talking about floats, float to float to float, etc. Same for minus, times, a couple others that I omitted for brevity. And then num also has a from integer from method rather, that is of type integer to A. And I included that because you can't do that in Java or in C++, because C doesn't have classes. You can't do it in Java, you can't do it in C++, you can't do it in basically any language that I know of, at least, that has interfaces or whatever the language's equivalent is. And the reason for that is this takes an integer and it produces a member of our type class. It does not take a member of our type class. So we couldn't express that in Java, for instance, as our type dot from integer. You can do it in Haskell type classes because they're more general. Does that make sense before I continue? Yes?
So what exactly would be the full use of this?
Good question. That's coming up in the next slide, or 2 slides from now. There's still a bit more background first. If I haven't answered your question in 2 slides, ask it again. Did you have the same question?
It was a similar question, but I'm sure it'll be answered by.
Okay, if it's not, ask it. So this is how you define a type class, great. But that's not terribly useful on its own. Obviously, you need to put things into the type classes. And we do that with instances. So for instance, we would say instance num, my type, meaning my type is a member of the num type class, same as implementing a method, an interface in Java. And then we define all of the things that it requires us to define. That part is fairly straightforward. I'm not going to include the actual definitions because obviously they depend on the particular type we're using, and I haven't actually defined my type. But they get defined the exact same way as any other function. They just happen to be inside a type class right now. And now we're actually using them. So here's our num type class from before. Suppose we have a function double then add one. Very useful function, I'm sure you see it all the time. Double then one, double then add one, takes a parameter, doubles it, and then adds one. What type should this have? So we could say, what type does this have? We could say that it's int to int, because if we put an int in, we get an int out. We could also say that it's double to double, because if we put a double in, we get a double out. But neither of those are really general enough to express what it actually is, right? So maybe we should say A to A, but that doesn't quite work either. That's too general, because what if we put a string in? We should get a type error if we put a string in, because you can't double a string and then add one to it. That just doesn't make sense. This isn't JavaScript. I make fun of JavaScript. I also make fun of other languages. Don't be offended if you actually like JavaScript. I just feel the need to put in that disclaimer because sometimes people don't realize that I'm not actually super serious about it. So the answer to this obviously involves type classes because that's the section it's in. And the way we do it is we say num A, fat arrow, A to A. And so what this is saying is double then add one has type A to A as long as A is a member of num. So if A is a number, then we can do this. If A isn't a number, say because it's a string, then you can't. And so that fat arrow is usually read implies, can be read other ways. I personally say implies, so I'm blanking on what the others are. But it basically means these are not actual parameters, so it's not a normal arrow. These are a context to the function type. Does that make sense? Does that answer your question about how do we use them?
Yeah.
Cool. Any other questions? Yes.
So this isn't a function that belongs to a type as we would conventionally think of something like in Java. Is it still
Correct.
closer to C almost?
So yes, this is. However, the plus minus times do belong to that type.
Right, okay. Right, because they take in that.
Because they're members of the type class. This is just a function that uses that type class.
What about from integer?
From integer is also associated with the type.
Would you do a dot from integer? Or?
You would not.
Okay.
The way you would do it is you would say from integer 3, and then using type inference, Haskell would figure out, oh, you're using this in a place that expects a foobar. So obviously you're looking for the from integer that's a member of from foobar.
So is it being in a class almost markup?
Yes and no. I told you I'd use that answer a lot. Yes, in the sense of you can do it without, but no in the sense of this gives you a lot of power to do things. For instance, like I alluded to earlier, you can have a function, for instance, double then add one, that works on numbers. And this works on any number type. Even if I define a number type after you've written this code, this will still work on that number type, even though you had no idea that it existed when you wrote that code. And obviously that's a simple example, but for something more complex, that's actually relevant. Doesn't matter so much for numbers, but if you were to write a complicated thing, for instance, just a project that I'm working on right now, if you have a type class representing an instruction set for a computer, you know what I'm talking about, then it's useful because I can write code that works with an arbitrary instruction set and then implement particular instruction sets before or after that, and it'll still work. Does that answer your question? I forget what the original question was. I've kind of just...
It answered it to me, yeah.
Okay. You can always ask me later if it didn't actually. Okay, cool. So that's all of the basic syntax. There is a bit more, but most of it you won't run into on a daily basis, and you can look up. The exception to that being record syntax, don't look it up, it's bad. I will talk about that afterwards because it has come up and I have to now. But I'll talk more about that later. Anyway, moving on to built-ins. Haskell obviously has a lot of built-in stuff. I've been talking about that, how everything in the kitchen sink is built in, kind of like Emacs in that respect. You've got a lot of primitive types. A couple of the common ones, char, int, integer, which is an infinite precision int. Int is 64 bits in particular. Integer can be as big as you need it. It's a big int in most other languages. Notably, most other languages have it as an external library built into Haskell. You have doubles, you have floats, you have strings. Actually, you don't have strings, just kidding. I'll get to that in a second. You have a lot of stuff built in. There's more than just those are the common ones. We also have bool, for instance. Bool is actually not a hardwired type that's built into the compiler. Bool is actually defined in the prelude, which is the standard library of Haskell. And it's defined as data bool equals true or false. Exact same way we defined shape up earlier, but simpler. And should have used this as the example. These are true and false are just data constructors that don't take any parameters instead of our rectangle that took 2 and triangle that took 3. These just is. Both true and false give you a value of type bool. So if you were confused about shapes before, maybe this will help. Maybe it just makes things worse. If so, sorry. Forget I said that. We also have the rational type, for instance, that is also built in the sense that is in the prelude, that is fractions. And it has fractions to arbitrary precision. You can do 5,387 over some other large number. And it will do that exactly. It won't round, it won't truncate like it would if you were using floats or doubles. You've also got tuples, which I didn't include here, but like a comma b in parentheses. You have those in a lot of languages. Python, Java notably don't. Also sometimes called pairs in Java, I think. It's basically just two types mushed together. So for instance, someone, I forget who, had asked about if you wanted to give a shape a color. And I said you can do that by declaring a new type that is colored shape. You could also just do it as a tuple of color and shape if you don't want to explicitly define a type for that. And then tuples can also grow to as many elements as you need. You can have a 3 tuple, 4 tuple, or 27 tuple. Don't have a 27 tuple, that's a sign of bad code. But you could, you just shouldn't. And then you can also have a size 0 tuple, like that. And that is actually called unit, because believe it or not, it's actually important in Haskell. And so we read that as unit. The type signature looks like open parenthesis, close parenthesis. The value of it looks like open parenthesis, close parenthesis. They look the same. Don't let that fool you. They're actually distinct things. That's the equivalent of void in most other languages, at least languages that have void. For instance, if you want a function to not return anything, you have it return unit. And as to why that's important, why would you want a function to return nothing when you can't have side effects? I'll get to that. But just know for now that that is a type that exists. We also have parametric types. This is what tuples are. I didn't forget them. Parametric types are like our second shape example before, types that take other types. Some built-in ones are lists, obviously. Lists are super important in functional languages in general, Haskell specifically. And so this is actually a little bit of syntactic sugar. You can't normally define types that look like this, but lists are important enough that they get their own special syntax. And so the way you actually read this is list of A is either the top line is cons. It's saying, I can't point out that high. We're saying this guy const, with the colon means cons, onto a list of A's. Right? Is everyone familiar with what I mean when I say cons? Cool. Just wanted to make sure you got at least that far in bracket. Or you have the empty list, also known as nil, if you come from a list background. Or bracket. Bracket might also call it nil sometimes. That's why I really dislike bracket, is because they got rid of nil and cons.
Nil being the empty list?
Nil being the empty list, yeah.
Yeah, it's empty.
Yep, it's called empty in bracket. And that's why I dislike bracket, is because they took it out. Like, they could have added, and I'm rambling. I'll complain about that later when I'm not being recorded. Another parametric type is maybe. This is actually really useful. It's basically the equivalent of nullable things in other languages, except it's typesafe. So you don't get null pointer exceptions. And so basically what this is saying, exactly what it says on the tin, a maybe A is either just an A, meaning it's not null, here's the thing, or it's nothing, which is your null equivalent. And the reason this is better than having null is because maybe A is a different type than A. If you try to use one in place of the other, it will throw a type error. So you can't have null pointer exceptions because it just won't compile anything that could lead to a null pointer exception. In Java, more recently, I believe you can tag things as nullable, and then it will do some stuff to make it more like this. Also in Java, either 8 or 9, they introduced optionals, which are gimped maybes. But because it is such a valuable thing, and I'm rambling, but it's cool, and type safe. And, okay, there we are. We also have the type either, which is saying it can be either an A or a B. And so, we have either left A or right B. And again, this is like a type-safe version of not being type-safe, where you can say in JavaScript, for instance, you can return an int or a string or an object or a foobar from a function. And that's entirely valid in Java. In Haskell, it's not. But in Haskell, you can say I return an either int string, meaning I return either an int or a string. And then you can, in a type-safe way, work with that. So when you call a function, for instance, that returns that, you can then get the result and then pattern match it on it, like we talked about before, and do something different if it's an int versus a string, or somehow fold them together based on your particular use case. But it's not the same as just returning either one, because it's type safe, and you can tell at compile time which one you have. Does that make sense? Cool. Okay, here are the common built-in functions that I talked about. Again, there are a zillion of these. You can just look up the docs for the prelude if you want to see more of them. But some common ones, we've got comparisons, equals, not equals. Interesting to note, not equals is not bang equals like it is in most languages. It's slash equals to look like the not equals sign from math. Because Haskell is very much based on mathematical principles, and so it uses the more math-like notation. You've also got less than equal to, greater than equal to, et cetera, et cetera. We've also got arithmetic stuff. You saw a bunch of these before in the num class. Not all of these are actually from the num class. The division, for instance, is from the fractional class, because it's possible to have, this is a bit of a digression, but it's possible to have numbers that can't be divided. For instance, integers. You can't actually divide integers and get another integer. Right? You can say, okay, do a division with flooring, or with rounding, or with ceiling, but division itself on integers isn't actually well defined. And so you can't do it in Haskell. The Haskell actually has several different types for numbers, num being the most basic of them, but there are more. For instance, fractional, which contains the division. We've also got the caret for exponentiation, like you've seen before and someone asked me about. You've also got double caret and double asterisk, also for exponentiation. The reason for that is they all have different types. And I hear you asking, why would you want multiple ways? Why would you want 3, let alone 2 ways, 2, let alone 3 ways to do exponents? Doesn't that seem like a bit overkill? And the answer is they're all different ways of doing it. For instance, the single caret requires that the power be an integer. And so that means, for instance, if you're doing 2 to the 3, it requires that 3 is an integer. And so that means that you can do it, you can implement it just in terms of multiplication. So your base only has to have multiplication at 1/2 power. You wouldn't be able to do that using single caret. Because for ints, for instance, you just can't do that. What's the square root of 2? Well, it's not an integer, so you shouldn't be able to do that on integers. Double caret is a bit more general. It also lets you have negative exponents. Again, not something that's useful on integers, for instance, but it's useful for anything that has division. And so that is again built on things that use division. And then the double asterisk is for arbitrary exponents. If you wanted to do, like the square root of 2, 2 to the power of 1/2, you would use the double asterisk for that. And so these are, in some sense, listed in increasing order of power. In some sense, they're in decreasing order of power, depending on how you look at it. On the left is the most general, but the least, but can be used in the fewest ways. On the right, you have the thing that can be used for the fewest things, but in the most ways, if that makes sense. Cool. Does that actually make sense, or are you just humoring me? Excellent. Some more built-in functions. We've got logic stuff. We've got double ampersand for and, double vertical bar for or. We've got not for not. We've also got functions and spelled out as a word or spelled out as a word that take lists of Booleans rather than just 2 Booleans, which again can be useful. We've also got a lot of list manipulation functions because lists are super important in Haskell. We've got ++, which you've seen before, appends to lists. And so before, when I said that it was a string thing, that was actually a little bit of a lie. Because strings aren't actually a thing in Haskell, per se. Strings are just lists of characters. And so everything that works on lists automatically works on strings, because strings are lists. Strings aren't a separate type. They're just an alias for a list of char. We've also got map, which hopefully you're familiar with from Racket. Filter, which maybe you're familiar with from Racket. Doesn't do back a slide. We've also got folds, which I didn't include here. Are you familiar with those from Racket? Excellent. We've got a whole lot of folds, fold left, fold right. Yes?
Sorry, I'm going to swear the square braces indicate?
Lists, sorry.
Oh, right.
Yeah, no, that's my bad. Square brackets are lists of whatever's inside them. So for ++, we have a list of A's, taking 2 lists of A's and producing another list of A's. And the other neat thing about type signatures is when you have functions that are written well, you can tell what it does from just the type signature. For instance, say you had never seen the function map before, you didn't know what it was, you can look at that type signature and say, okay, it takes a function from A to B, it also takes a list of A's, and it puts out a list of B's. I wonder what that does. This is the only thing it can do, because it doesn't know anything else about the type A. It doesn't know anything else about the type B. All it knows is that it has some of them, and a way to get from one to the other. So that's all that map could be, is what you're familiar with map being. There is nothing else it could do because the type signature constrains it. And that's actually a really powerful thing about having such a strict type system, is that a lot of the time you can tell what a function does just from its type signature. And then even more so from its name and type signature. Some more common functions, if this mouse will work. ID, which is short for identity, is just the function. It takes a parameter and it spits it back out. Obviously not very useful on its own because you can just do that without the ID. But it's very useful in higher order programming, meaning when you have functions that expect functions, for instance, map or filter. And so suppose you are using a function that's expecting a function as a parameter, but you don't really want to give it a function. You want to just have it work on the things itself. You just pass an ID for the function, and it will use that. So you don't need a separate version of each. We've also got const, short for constant, obviously. You can look at it two ways. Either it's a function that takes two parameters, ignores the second one, and returns the first, or it's a function that takes a parameter and returns a function that ignores its parameter and just gives you the thing. And in some sense, yes, that's just restating what I said earlier about how there aren't actually multi-parameter functions. But it's also useful for const in particular because those are both semantically valid ways to use const. Its argument and returns 3. There you are. You don't need a separate version of that function to only use integers. You can just give it a const. Flip. Someone asked a question that involved flip. I don't think that person's here anymore. That's unfortunate. If you're watching at home, flip. Flip does basically what I said before. It takes a function from A to B to C, meaning it takes an A and B and produces a C, and it turns it around and gives you a function that takes a B and then an A and then a C. So if you want to apply parameters in a different order, you use flip, or you use lambdas, either one. Whatever makes the most sense for your particular use case. And then the cache operator. This is really no different than any of these, or ones from earlier on. But it's so immensely important that I gave it its own slide. So first, just looking at the type. It takes a function from A to B, and it takes an A, and it gives you a B. Any ideas as to what it does? This is not a trick question. Also, the answer is right there. It takes a function and a parameter and applies the function to the parameter. Whoop-de-doo. By itself, again, not super important. You can use it in higher order programming. It does absolutely have purposes there. I've used it in that way a couple of times. But it's not all that useful there. Where it really shines is when you have code like this. Foo equals var for parentheses as some text, quux 1 plus 2. Very technical code, copied from my senior thesis. That's a joke. This looks awfully Lispy, and Haskell is not Lisp. Haskell does not like parentheses as much as Lisp. And so what the cache operator lets you do is it lets you replace parentheses, like this. So what this does is we have, looking at just this bit, quux 1 plus 2. We have quux on this side, and then 1 plus 2 on this side. And because of the order of operations that's defined for the cache operator, everything else happens before cache. So 1 plus 2 gets evaluated, and then quux gets evaluated on that. Yes?
It's maybe kind of a weird question, but how can you tell that baz is another function instead of a second argument to bar?
In which one? First one or the second?
The second one. I mean, the first one, kind of the same thing, but it's at least to my eye, it's easier to tell.
Yeah. So the first one, it's because of parentheses.
Yeah.
The second one is because function application binds tightest of all. So you do function application before you do any operators.
Mm-hmm.
And then the first operator that you always do is the cache operator.
Got it.
Or the last one, depending on whether you're doing recursive descent or ascent. So we have quux 1 plus 2, where if we didn't have that $sign, it would be parsed as parentheses here, quux 1, and then we add 2 to whatever that is. But this way, you know, we have the parentheses, so it does it this way. And then we say the cache operator is also defined. $sign is pronounced cache, by the way. Not sure if you picked up on that or not. If you didn't, very sorry for the confusion. The cache operator is defined in terms of precedence so that it is left to right. So that this one comes before this one, comes before this one. And so this code is exactly equivalent to one one, except easier to type and easier to read once you understand what's going on. Definitely not easier to read to a newcomer. I will not try to deny that. But once you're used to it, and it happens all the time in Haskell code, so you'll get used to it pretty quickly, it's very, very useful. Any questions?